All right. So, hello everyone. Hi again. So for today, our last talk for our webinar, or sorry, yeah, webinar slash workshop here, is from Mr. Deepak Bakal. He is a PhD student about to graduate. Congratulations in advance. From Savitribai, Pune University, Pune, India. I hope it's correctly said. And he's gonna talk on their problems with past algebras. So, hi Deepak. You may now
So,
start.
hello everyone.
Hi.
Hi.
So, is my screen visible?
Yes.
Yeah, but probably it could be
Bigger.
bigger, yes. Or maybe this is a iPad, I think you're using.
There.
Okay.
Yeah,
Good,
yeah.
good. Thank you.
So, thank you for the opportunity. So, today I will be talking about the title of the talk is Baer rings and clean ring properties of Leavitt path algebras. Uh, so, Leavitt path algebras with directed graphs, sometimes also called as quivers. So, to each quiver, we can associate a path algebra, and we can take quotient of that path algebra by some relations, and in this way we get a Leavitt path algebra. So these algebras were introduced by Jean Abrams, Aranda Pino, and almost simultaneously by Pereira, Moreno, and Pardo. They were introduced as algebraic counterparts to graph sister algebras. And there were generalizations of Leavitt path algebras. So of Leavitt algebras, the algebras which do not enjoy the invariant basis number property. So some sort of dimensionality we want to give to the modules, that thing fails in case of Leavitt algebras. So Leavitt algebras were defined in 1960s, but the interest in these rings came out in somewhat in 1980 when a similar structure was found in functional analysis called graph sister algebras, and they were again brought back into the algebraic avenues uh, through the Leavitt path algebras. They were introduced in 2005, and it's about now close to 2 decades, and the Leavitt path algebra is a very hot research topic. There are various directions and approaches for Leavitt path algebras. I mean, just two talks before we see that it is associated to talented monoids. The other approach that we see was through groupoids, and the third that I know is through inverse semigroups. So there are various directions of Leavitt path algebras in which the research is going on, and one important direction that Leavitt path that is going in this area is what happens is we have a graph E with a certain vertex set, edge set. Edges are defined by the source and the range, and to this multi-digraph or to this quiver we associate a Leavitt path algebra. So it is natural. So when we associate one object to other, we have a combinatorial object on one side, and Leavitt path algebra is an algebraic object. By algebra I mean a ring as well as a module. Let us fix some field K, and it will be a module over a field K. So it is natural to ask if the quiver has certain properties. What is the analogous property that we can get in the algebraic avenues? Or if Leavitt path algebras has certain algebraic property, what would be the corresponding combinatorial property? What would be the corresponding graph theoretic property? So the research direction is something like this. LK has a ring theoretic property Q if and only if the graph E has a graph theoretic property Q. And a lot of progress was made on this. In particular, simple Leavitt path algebras were characterized in terms of Leavitt path algebras. The one that I can immediately tell is Leavitt path algebra is Noetherian, and we had seen previously that commutative rings enjoy invariant basis property. So whenever we talk of Leavitt path algebra, it's always clear that we are in non-commutative setup. So it doesn't matter whenever I say Noetherian, you can fix something like left Noetherian or right Noetherian. So Leavitt path algebra as a ring is left Noetherian if and only if the graph has finite number of vertices and no cycle has exit. I'll define what no cycle has exit means later, or maybe I can like intuitively it's something like this. Whenever you have a cycle and you can go from this vertex to this to this to this, and if we keep on looping in the same, that means it has no exit. But suppose there exists another edge and which takes us to another vertex, you can come from this vertex to this vertex, and instead of going to cycle you can come back. So we will say that this cycle has exit. So this characterization again was given by L.Vas, but the talk that I'm today. So two important classes of rings are Baer rings and clean rings, and it is natural to investigate these two classes for Leavitt path algebras. So the natural question that we would like to ask is which Leavitt path algebras are Baer or which Leavitt path algebras are clean as rings, and we will see what Baer means. We will see what is clean means. Just pardon my pronunciation. This Baer is pronounced like this, probably like Baer, but everyone in my vicinity pronounces it as Bayer. So I know it's some sort of wrong pronunciation, but I have got used to it. So please pardon my pronunciation. So these two classes have been researched extensively over last few decades. Clean rings were introduced somewhat in 1980s, and Baer star rings goes around 1950s. And the interest in this two Leavitt path algebra in the Leavitt path algebra scenario, the interest is due to the mathematician L.Vas. So she is a pioneer in the area of Baer star rings, and her paper got me interested into the Leavitt path algebras. So let us see what is a Ricard ring or and a Baer ring. So from a historical perspective, the mathematician von Neumann this rings emerged from the consideration of operator algebras by Kaplansky and Ricard. Kaplansky and Ricard used to work in functional analysis, and they what they did is whenever they had some C star algebra, they wanted to extract certain properties. So like they had some C star algebras and AW star algebras. They wanted to abstract those properties. They wanted to take away this C star algebras as three structure: algebraic, analytic, and topological due to the norm on it. But what they wanted is they wanted to get rid of analytic and topological aspects, and they wanted to abstract away only the algebraic parts. So this is called as that this term was coined by Leah herself, algebraization of operator theory. So many mathematicians worked in this area, including Kaplansky, Ricard, von Neumann, and Barbarian, to name a few. And Barbarian in his book remarks that like we want to take away all the analysis, and what would remain is algebra. So let us see what it means. Let us see what is a Ricard ring and what is a Baer ring. So fix a ring R, let X be a subset of R, and consider right annihilator of a set X. So for example, if you have an element X coming from X, we want to annihilate it from right. So X into R is 0 for all X belongs to X. Then we say that R annihilates X, and since R lies on the right side, we will say that R is a right annihilator. R is the right annihilator of X. Similarly, if Rx was 0, we would say that R was the left annihilator. Now it is straightforward to check that right annihilator and left annihilators are ideal, and right annihilator would be right ideal. For example, if I have an X, if something R annihilates it, then X into R into another element R dash, it will also be 0. And if X into R1 is 0, X into R2 is 0 for two different elements, R1 and R2, then R1 plus R2 is also 0. So it is clear that right annihilator is a right ideal. Left annihilator would be analogously would be a left ideal. So if I have a set X, and if I consider the right annihilator of this set X, so sorry, right annihilator of X, and if it is generated by an idempotent as a right ideal. So this is generated by an idempotent E, which is ER. Then such a ring we will call it as a Baer ring. And if this X was singleton X, then such a ring would be called as a Ricard ring. So in some sense, not in some sense, this is actually true, that Baer ring is a specific example of a Ricard ring. And some trivial examples would include fields, integral domains, and the motivation was C star algebras. A finite analog of that is matrices. So MNC is an example. So we have left Ricard ring, right Ricard ring. Whenever the annihilators considered are left annihilators or right annihilator. If you consider right annihilator and it is generated as a right ideal by an idempotent, then we called it as right Ricard ring. Similarly, right Baer is defined, and you can define left Ricard and left Baer, considering the left annihilator of an set or an element. If you are considering set, you are into the Baer setup. If you are considering points or you are considering singleton elements, then you are in a Ricard setup. Now see this. If a ring is right Ricard, then the idempotent will generate the right annihilator of 0. So something like this. What would this be? Annihilator of 0 would be the whole ring R. But then this has to be generated by some element E. And now thus this E would act as an identity. And hence Ricard rings are necessarily unital. So in the definition of Ricard ring, we need not assume that they have an identity. It's a consequence. Now we are into another thing. Whenever we talk of C-star algebras, they are equipped with something called as involution. So what we will define a ring with involution. So a ring usually ring has two structures: addition, multiplication, and here we have an additional structure R. So R star is a function from R to R, such that if I consider two elements A plus B and I will take their star, then it is A star plus B star. And if I consider A B star, it would be B star A star, not A star B star. If it were A star B star, then it would be an homomorphism. So for this reason, it is called as anti-homomorphism. So a ring with involution is basically a ring with an anti-homomorphism, which is an automorphism. So we will see what there is an important operator in functional analysis called projection. Projection is basically an idempotent which is invariant under this star. So if you have an element which satisfies x square equals to x star, such a thing is called projection. So it's a special case of idempotent. And so whenever we go from a normal ring setup to a involutive ring setup, we will always replace idempotents by the projections. So we will have analogous definition of Ricard star ring and Baer star rings. So a star ring is called Ricard star ring if the right annihilator of a single element is generated by a projection. So PR, so that is PR star would be R P, instead of P star is P. So what this gives us is we get away from the concept of right and left. Intuitively see this as like if xy is 0, xy star would be y star x star equal to 0. So something which is annihilates on the left would annihilate on the right as well. So that thing is known as left right symmetric. So we will not have something like the left Ricard star ring or a left Baer star ring. We will simply have Ricard star ring or a Baer star ring. So let us move to some another class of ring called von Neumann regular ring. Von Neumann regular ring R is an associative ring with identity. It need not be commutative. Is a ring such that for every element A, there exists an element X such that it satisfies the equation A equals to AXA. So let's say if you have field, then for every A, you can have A inverse. then we can write A equals to A inverse into A. So you can think of this X as like weak inverse of A. So you can think of this as some sort of weak inverse of A. Now, since we are not necessarily in a field, it may happen that A into R is 0. A may become a 0 divisor. So in that case, A into X plus R, that would be A into A would be AXA plus ARA, but AR or RA was 0, then you would again get AXA. So inverses were unique, but the von Neumann inverse, the weak inverse, it need not be unique. So it is not uniquely determined. A property is that a ring is von Neumann regular if and only if every finitely generated left ideal is generated by an idempotent. And why do I need this? I need this to say that a VNR ring is a Ricard ring. So whenever you when I say that a ring is von Neumann regular, and this remark says that every finitely generated left ideal, so the annihilator would also be generated by an idempotent, and if annihilator is generated by an idempotent, it's called Ricard ring. So let's see a short proof of this. So consider an X belongs to ring R and consider the ideal generated by X, then it will be Re, since we are assuming that left ideal is generated by an idempotent. So X is Re, but E then would be Sx for some S. And then just try to do this XX, XSX, it would come as Xe equals to Re square equals to Re. Since E is idempotent, E square is E, and that would again come as X. So you can produce a inverse. So one part is clear. For the other part, suppose R is regular. Von Neumann regular. The term regular is highly abused in the literature. Regular sometimes mean von Neumann regular, and sometimes it is mean not a zero divisor. So we have to be sure, like, what does the author mean. Suppose R is a von Neumann regular ring, and consider I equals to Rx. Use Y belongs to R. Then, since we are assuming R is von Neumann regular, we can R is chosen such that X, Y, X is 0. So Y is weak inverse of X. So let Yx equals to E. Now why I am saying this is equal to E, you have X, Y, X. And if you multiply this again by Y, X, Y, X was X, Y, then X, Y becomes an idempotent. Similarly, if I multiply by Y on both sides, then I get Yx equals to Yx. So Xy and Yx are both idempotent. So this is an idempotent, this is an idempotent. So let Yx equals to E. Now Xe is X, multiplying X on both sides. Now if X belongs to Re, that means I is contained in Re. And if again, if I choose E equals to Yx, then I get Re is contained in I. So for our purpose, we are done. That generated by single element. A principal ideal is generated by idempotent. We will not go into the finitely generated. It requires a similar technique. But what I want to convey is that a von Neumann regular ring is a Ricart ring. So another example of a von Neumann regular ring is endomorphism ring of a vector space. So if you consider all the linear transformations from V to V, and if you they have a natural structure on that, ring structure on that, you can add them and you can multiply them, and like that you can compose them, then this ring is von Neumann regular. Why I had included this was this ring is also clean ring. We will see what clean ring is that, even though in the next of the presentation it is not mentioned, but I'll mention it here, that this example was taken only to convey that this is an example of a clean ring as well. I'll skip the proof of this for now because I think I might run out of time, so I'll skip the proof. So this lecture is more like definitions and what they mean. No proofs will not be given. So a special case of von Neumann regular rings is something called as unit regular ring. So if I have an element A, I can write it as A x A in a von Neumann regular ring. And if I can choose this X to be a unit, then such a ring would be called as a unit regular ring. So a unit regular ring is such that for every A in R, there exists a unit in R such that A can be written as A equals to AUA. And we will have a notion called as locally unit regular. So locally unit regular, for this purpose, instead of having a unit, you will have local units. We talked of this, I think Alfie talked about it before my lecture, local idempotents and local units. So nevertheless, the local units, they are basically the idempotents, and the conditions are like this. So R is locally unit regular if for each A in R there exists an idempotent. So there is no unit, instead there is idempotent such that A is in VRV. Okay. So if V is idempotent, VRV is called corner of R. Such a thing is also called as corner of R. So because we are multiplying these two things on the corner, somewhat sense. So just note this. So there exists an idempotent in corner, and there are two elements U dash, such that U into U dash equals to V equals to U dash A, U dash into U, and the usual thing that A equals to AUA has to hold. Such a thing is called locally unit regular. And G. Abrams and K.M. Rangaswamy, they proved in this paper called Regularity Condition for Arbitrary Leavitt Path Algebras. This was published in Algebras and Representation Theory Journal in 2010. They have proven that for unital rings, for rings with identity, the two notions coincide. So a ring is unit regular if and only if it is locally unit regular whenever the ring R has identity. Now, in the same paper, Abrams and Rangaswamy characterized von Neumann regular rings, properties of Leavitt path algebras. They said that a von Neumann regular Leavitt path algebras were essentially those Leavitt path algebras whose underlying graph E are acyclic. If there are no cycles in your graph, then the Leavitt path algebra would be von Neumann regular. In fact, they proved a little more. What they proved is they proved it is von Neumann regular. It is unit regular. We have seen what unit regular means. It is pi regular. Pi regular means instead of x, for every x, x raised to n, a x raised to n equals to a. So whatever you have for a, for x, you get the thing not for x but for x raised to n, then it is called pi regular. Whenever like you see pi in this setup, it's always been power of something would satisfy instead of the element a. And strongly regular means the a was chosen to be axa, and if this a and x commute, then a can be written as a equals to a square x. In such a scenario, we say that it is strongly regular. And something which strongly pi regular means instead of x, it would hold for the power of x. So they proved that it is von Neumann regular if and only if it is unit regular, if and only if it is pi regular, and if and only if it is strongly pi regular. And this characterization was given by them. Now, what we saw was from a ring R, you have a ring with involution, and in involution, the idempotents are replaced by projection, and they are more natural to deal with since we get rid of the terms left ring and right ring. So the concept of regularity was extended to star regularity of rings. So a star ring will be, we say that it is a star regular if the principal, every principal right ideal is generated by a projection. That means R is regular and the involution star is proper. So what we mean by a proper involution is, it means that whenever you have like x into x star is 0, that would imply x is 0. Or the other way around, if x star x is 0, then again x is 0. You can choose whatever you want to be. So the definition is, an involution is said to be proper if x star is 0, then it implies x is 0. For example, consider complex numbers. It has the natural involution of complex conjugation, and if you have a complex number z and multiply by z bar, then you get, let's say it's equal to 0, then you get mod z square is 0. That would imply mod z is 0. So this involution is proper. And if instead of this you have something like this x1 star x1, x2 star x2 plus xn star xn equals to 0, and all of them are 0, x1 equals to x2, then such a thing is called n proper involution whenever there are n terms involved. So natural to see that this involution is not n proper. So why we are interested in involution? Because Leavitt path algebras are naturally equipped with a involution. So this involution again was defined by Pune, Rangaswamy and Vas. So what is a typical element of an Leavitt path algebras? So we had seen that these paths were like pi qi star, and then we multiply them by some field element k, and we take their formal sums, and we want to define an involution star on this. So note that this star is different from this star. So what would be the natural way to think of this? We had this thing like a b star was b star a star, and a plus b star was A star plus B star. So if I were to do this, I would do it and A star is A. Sorry, I forgot to mention that. Example include trace of matrix. Sorry, I forgot to mention this condition. A star has to be A. So it is to say what is the term? Like second power is itself. I forgot the term, the name for it. So if I were to take the involution on this, that would be Qi Pi star. This two would be have go via this, and there should be an involution and on K. Fields are also rings, so they would also have involution. So if a field has involution star bar, then the involution would be defined like this, and that's explicitly how they define this involution. So consider this map on the elements of Leavitt path algebras. The involution we define is like this. It is straightforward to check that this map is indeed an involution. So the previous result was generalized, and what was proved that a Leavitt path algebra is star regular if and only if it is regular and proper, if and only if the graph is acyclic, and there is an additional condition. The K is n proper for every n. So this n less equals sigma. So sigma is the supremum of length of all paths if it is finite, or and if it is infinite, we denote it by omega. So a Leavitt path algebra is star regular if and only if the underlying graph is acyclic, and this field K has n proper involution, where n was the supremum of length of paths. Now they in the same paper they have proved this proposition that for an arbitrary graph, if involution is positive definite means that is it is n proper for all n, for all natural numbers. If it is n proper, then the involution is said to be positive definite. And if you have a positive definite involution on the field, then the involution star on Leavitt path algebras, it would be a proper involution. So there exists a like a very restricted condition on the for the field, and it gives a smaller condition on the Leavitt path algebras. And as a corollary, we obtained that involution is positive definite if and only if the Leavitt path algebra is star regular for every acyclic graph E. And due to this, we get the next corollary that says that for an arbitrary multi-digraph and for a field with involution, Leavitt path algebra is star regular, then it is locally unit regular. And if Lk of E is a unital ring, then in a unital ring, these two notions coincide, then it would be unit regular as well. So let us move on to what are Baer-Leavitt path algebras. So the results are taken from the paper by L.Vas and Hazrat. The paper was published in 2018 in Journal of Pure and Applied Algebra. So if you have a cycle E1, E2, E3, so on till En. So if you have a cycle like this, and suppose there exists an edge f such that the source of f, which is this vertex, is source of some other vertex, like there exists this E3 over here as well. So source of f is source of ei, or you can say source of ei is range of ei minus 1 for some I. So if such a thing happens, we say that this cycle has an exit. So this edge f is an exit for that thing. Like you won't always be trapped in a cycle. You can always get out of this somewhere from E1, E2, you can go to f and you are out of the cycle right now. So that's why it's called an exit for a cycle. So what they proved was that a Leavitt path algebra is Baer if and only if the vertex set is finite. Sorry, the graph is finite and no cycle has an exit. So if you have a cycle, there won't be an exit for that. You will always be trapped in that loop. And for going to Baer star rings, for rings with involution, we need an additional assumption that whenever you have a field K, that field has to be positive definite. And then the Leavitt path algebra is Baer star ring if and only if the graph is a finite disjoint union of graphs which are finite and acyclic. So they are acyclic graphs or loops. They are finite and they are loops only. So disjoint union of finite. So something like trees and loops. The next result is quite interesting. This says that LK of E is Ricard if and only if the vertex set is finite. E0 vertex set is finite. So most of the algebras that we would consider uh, are going to be Ricard only. Now for Ricard star ring, no such characterization is known. And this has been left open. Why I was interested in this topic, this is not in the slides, is because Baer rings and Ricard rings, they are generalized instead of considering sets, annihilators of sets, people consider annihilators of ideals. And such a thing is called quasi-Baer. And instead of considering annihilator of a set X, people consider annihilator of principal ideals generated by X, and it's called principally quasi-Baer. They have involutive analogs quasi-Baer star ring, principally quasi-Baer star ring. Principally quasi-Baer star ring does not enjoy the left-right property, if I'm not mistaken. And to the best of my knowledge, this is also open. For quasi-Baer star rings, I think one condition is known, but characterization is not known. So this problem is left open. And that's what had brought me interested in this area. So this question is open. And for this, we will need to do a little bit more literature survey. But I think it is open. And there is something called as pi Baer rings, which are recently defined. So instead of considering the annihilator of any random set S, you consider a projection invariant. If you multiply ES equals to S, such a set is called projection invariant. And if you consider the annihilator of this and it is generated by projection, it is called as pi Baer. So this sits between Baer and quasi-Baer properties. And definitely only the defining paper has come, but LPAs are not known. So this could be of interest to us. So these are the questions that I propose. Now moving to clean rings. Clean rings can be considered as additive analog of unit regular rings. So let us recall what is a unit regular ring. A is called unit regular if A could be written as this form, A equals to AUA. And now we have seen that AU and UA are both idempotents. So A equals to, let's write it as U inverse equals to U inverse UA. Now this AU is an idempotent E, U inverse equals to this UA is again an idempotent E dash U inverse E dash. So you can write A as product of idempotent and a unit. Uh, like what comes first doesn't matter, but you can always write A as an product of an idempotent and a unit, and so that is another definition of unit regular rings. So A equals to U into E. So let us consider the case where A is U plus E. This would be an additive analog of unit regular rings, and such rings are called as clean rings. The term was coined by W.K. Nicholson in 1970s. And the first paper had this example of the endomorphism of vector spaces that was later generalized to the division rings. So example of clean rings include a local ring. So for example, a local ring consists of a maximal ideal M. So if you have an element, it would either be from a maximal ideal or it won't be from a maximal ideal. And if it is not from maximal ideal, it would be a unit. So if it comes from here, you can write it as unit plus 0, which is an idempotent. And if it comes from the maximal ideal, you can consider A minus 1. Then A minus 1 would be see this A minus 1 plus A, sorry, is equal to minus 1. This would be the whole thing R. So clearly A cannot be in the maximal ideal if A minus 1 was in the maximal ideal. So you can write this A as A minus 1, which is a unit, plus 1, which is idempotent. So you have got local rings are clean rings. And if you consider the direct product of local rings, you just have this addition and you have to separate the multiple elements into an idempotent unit is if everything is unit, and idempotent is if everything is idempotent. So naturally the product of local rings would be a local ring and hence a clean ring. Yes. Am I making sense? No, I think I said something different. The product of local rings need not be local, but yeah, the product of local rings is a clean ring. You have like idempotents. You can separate out idempotents. You can separate out units, and this way you can get the split of unit plus idempotent. This guy is idempotent. This guy is unit. So they need not be local, but yeah, they are clean. And so Artinian rings are such rings. So product of local rings, Artinian rings are special cases of that. So Artinian rings are also clean rings. And matrices over local rings, sorry, matrices over clean rings are clean. So that also includes an example of clean rings. So we had seen that this clean rings emerged as additive analog of unit regular ring, and there is a celebrated theorem called Camillo-Khurana theorem, which says that unit regular rings are clean rings in which an element can be decomposed as a sum of unit plus idempotent such that an additional thing holds, that AR intersection ER is 0. So AR intersection ER equals to 0, such a thing holds in unit regular rings. So in some way these are special clean rings, because this condition is a very rigid condition. And if this condition holds for an element which can be written as, we will call such an element as special clean element. Now,
I think Deepak got disconnected, so we will wait for a bit.
Yeah.
So T.Y. Lamb in a conference in 2005 had asked a question, which von Neumann algebras are clean as rings. So to answer this question, Leavitt, she defined the concept of star clean rings where idempotents are replaced by projection. Since von Neumann algebras are naturally equipped with involution, so that was her motivation to start this work. So star clean if it is an unit plus projection instead of idempotent. You will call a ring as almost clean if it is unit plus regular, regular in a sense, not in one Neumann regular, but something which is not a zero divisor, neither left zero divisor nor a right zero divisor. So she proved certain properties connecting the Ricard landscape and the star clean landscape. And what interesting thing is that the question to characterize clean rings is still open. I mean, to characterize clean rings and star. So the Leavitt path algebra characterization is not known. Interestingly, the graded versions are known. They have defined the graded versions of graded clean rings, and the graded characterization is known. The graded characterization is something like the graph is either dots or dots with loops. But the characterization of a clean ring is not known. The Leavitt path, which Leavitt path algebras are clean, is not yet known. Nothing is known about the star cleanliness. We had seen that the certain matrix algebras MNK emerged and they are clean. So there are ample of examples of clean Leavitt path algebras, but characterizing condition for the clean things are not known. The graded versions are known. The graded versions of Baer and Rickert are also given in the previous paper. Something called as local versions, where instead of ring R, you consider the corner ring ERE. Then that was also done in that paper. So the other things are also known, but these are the main problem here is to characterize clean Leavitt path algebras, clean and star clean. So with this, I stop my lecture. Thank you, everyone.
Yes.
Thank you, Deepak.